The plan of my talk is the following. So first, I will present Carl Hermann's theorem on integrability because it's a bit different from the finite dimensional case. And then I will give two methods of integration: Lie algebra extensions to Lie group extensions via path groups or via prequantization extension. So we seen yesterday the Lie algebroid cohomology. So the Lie algebra cohomology is a special case of this. So I wrote here for the complex is the we are in the infinite dimensional setting. So the Lie algebra is Frechet, and we take continuous cochains psi on the Lie algebra, and here is the Chevalley-Eilenberg differential. It is well known that the second cohomology of the Lie algebra classifies continuous central extensions. This is written for one-dimensional central extensions of G by R, but sometimes it's useful to have also central extensions by a bigger center. So I will denote by Z the center. So we take Z-valued two cocycles. So I wrote there the cocycle identity. So is this cyclic sum has to vanish. Given such a cocycle, we get central extension of G by R by the bracket that is in the middle of the slide. And if it's the boundary, then here's alpha is a sigma, or sigma and alpha. If it's the boundary of alpha, then alpha gives us the, with alpha we can build an isomorphism of the central extension given by psi with the trivial one. That's why I wrote again here as a theorem the Lie algebra cohomology, continuous Lie algebra cohomology with values in Z parameterizes isomorphism classes of central extensions of Lie algebra G by the center Z. And I'm writing again what a central extension is because it's a tutorial. So there is what is a continuous central extension of G by Z. We have such a exact sequence, which we ask to be topologically split so that we have an associated continuous Lie algebra to cocycle. So with a continuous linear splitting sigma from G to G hat. So the cocycle is just measuring the failure of sigma to be a Lie algebra homomorphism from G to G hat. This difference is in the center. One can check it. On the group level, we have smooth central extensions of G by an abelian group Z. Similarly, an exact sequence where Z is central in G hat. And we ask for smooth sections, but it's enough to have them local smooth sections. In this way, G hat becomes a principal Z bundle over G. And the associated group cocycle, which is a priori defined locally, but one can extend it. It's this, again, measuring the failure of S to be a Lie group homomorphism. And how does a Lie group 2 cocycle define a central extension? On Z cross G, we have this multiplication, which is altered by the group cocycle. That's why projective representations of G correspond to linear representations of central extensions of G hat. The co-cycle condition is written in blue, and we consider one can normalize the co-cycle such that C of GE and C of EG is 1. And yes, since they were require smoothness only in the neighborhood of the identity. What is a co-boundary? Written there, this is the co-boundary of lambda, and when it is a co-boundary, then it defines a central extension that is isomorphic to a trivial one on Z cross G. And a similar theorem that this Lie group cohomology parameterizes isomorphism classes of smooth central extensions, which means extensions that admit local smooth local sections. And one can pass from a group co-cycle to the Lie algebra co-cycle by twice differentiating. Here is the formula. And I'm giving an example, the nice one, Virasoro-Bode group, when you really have a group co-cycle, when you can write the group co-cycle, a smooth group co-cycle on the Lie group. The group is the group of orientation preserving diffeomorphisms of the circle. And with Lie algebra, the Lie algebra of vector fields on the circle, and the famous Virasoro co-cycle, psi, has been later found that it is also the group co-cycle due to both has been found a bit later. So we can, when passing from the group to co-cycle to the Lie algebra co-cycle, so I denote it here by D, so it is part of a longer central extension. Thank you. And here in P we have the two obstructions. We can see the obstructions are in pi 1 of G and in pi 2 of G. And this is the 2004 theorem of Karl Hermann. So what are the two obstructions? The first obstruction is the one in pi 2 is given that by the period group. So there is a period, the period map, which is obtained by integrating psi L over spherical cycles in G. So psi L here is the left invariant 2 form on the Lie group, G, uniquely defined by the cochain psi. And since psi is a co-cycle, the psi L is a closed 2 form, left invariant 2 form on G. And so this is the period group. So only the spherical periods are playing a role. And one obstruction is that the period group is discrete, so that we can factorize it, factorize Z by the period group and get a nice abelian Lie group in the center. And then the other obstruction is the flux homomorphism. The flux homomorphism is, of course, vanishing if G is simply connected. So it has values in the linear maps from G to Z. It assigns to an element in the Lie algebra the integral over a loop of this one form on the group that is obtained by contracting the left invariant to form by the right invariant one vector field on G. So this is the integrability theorem. It's hard to apply it. Sometimes it's hard to apply to a concrete cocycle. I will give an example, which is still an open question for the Hamiltonian diffeomorphism group.
The previous slide again shows where these two maps appear. So these are in P, right?
So here in P, we have the two maps. One is given, here is given by the, oops, it's, I wrote them wrongly. Here is the pi 1.
Ah, okay.
Yes, and here is the pi 2 into Z. So we factor out the period group, group. Okay, okay, so it's pi 2 and pi 1. It's a mistake. So here is one, P is built out of the flux homomorphism and of the period homomorphism, but now it is taken with V values in Z modulo pi psi. So if this vanishes, then the map before this one then vanishes. Yes, but here is the 2 and here is the 1.
But I still don't see.
So P of the class of psi. So this one is so let's take the first one as the period. Maybe I switch that to the next. So it's here period homomorphism, but it's modulo. As the values in Z, and the second one is the flux homomorphism. So this is from I1G into LGZ, and this is from I2G into Z. We take a Z and here a pi, and we ask that pi is containing the pipe size of we get the period vanishing. So this was my first section. In the second one, I will pass quicker because I will want to have time for the third one. So this is integration via path groups. So, in the special case, so this Van Est method, I don't know if I is when we have a discrete period group, so that's this one vanishes. But we have a family of smooth paths in G, like a natural given one, from E to each element in the group. And then we take these triangles with boundary FAG minus AFG plus AF. So these are these smooth paths. And we integrate the left invariant to form over this triangle. And C is not yet a group cocycle, but this expression is an integral a spherical integral of psi L because um, the the boundary of yes, one has just to put together all the triangles where these are integrated and build a spherical two-cycle. So in this way, with the family of smooth path, we get a group two cocycle. But this has been applied, and then so, so this is the central extension that we get by that group cocycle. And now, if the group cocycle can be resolved over a subgroup H, we want to have H a normal subgroup. So if it can be resolved, then basically it is trivial over H, but we need this extra condition which ensures that so the graph of lambda minus 1 gives us here the inclusion. And we want to factor out this subgroup, and it should be a normal one. And this is the relation, I think it's equivalent to it being a normal. So then here we factor out H, here we factor out this subgroup via this lambda minus 1, and we get a central extension of G mod H. And this is this type of, this method has been applied to the path group. I just send you first, show you first the same diagram, but now for the path group. So this is our former G, this is our former H. So it's the path group, and it's the group of loops that are contractible loops. And the factor group is the universal extension of G. And so in this way, one can build central extension of the universal cover of G. And I will go now back to the definitions. So we have the path group, so the paths that are starting at E, and the Lie algebra similarity. And we have two groups that integrate the Lie algebra, the Lie subalgebra of loops. There are all the loops based off E, and all the null homotopic loops based at E. We have the central extension, so this one is the one that we are using. And now we want to integrate a Lie algebra cocycle psi on G, which we assume to have a period group, vanishing period group. Yeah. And here we will ignore this because we are using the universal covering group. So what we are doing, we are pulling back the cocycle to the path Lie algebra. It vanishes on the loop Lie algebra. And here we have a natural system of paths written here. This AG, which with the Van Ness method gives us the cocycle. And it's even the simplices are canonically given. And with the Van Ness method, one apply it and one finds a formula, not a very nice one, but still acceptable for the cocycle on PG. And here then we want it to be resolved over the subgroup over omega 0 G. And it is, we take any homotopy that, so remember G is null homotopic. So we take a homotopy from E to G in the in omega 0 G, and that's then we integrate psi L over this homotopy. So this gives us two in G, and we integrate psi L, and take out the modulo the period group, because otherwise it depends on the choice of G bar. Modding this out, it doesn't depend, and in this way one gets this central extension that integrates psi. But this, I wrote it in an old paper of mine, but it's actually, it was used for the loop group by Michelson, and then for the current group, you will see the next one. Here, I just want, so there are nice formulas. So this is the well-known co-cycle on the loop, on the path, on the loop group, or the loop algebra. K is the Killing form, but it can be extended to an z-valued invariant form, and then is the group co-cycle and the lambda that is. One finds this lambda. So here eta is the Cartan-3 form, and the Polyakov-Vizman formula that relates the pullback of the Cartan-3 form by the multiplication and the pullbacks by the projections. The difference is here an exact form. This it can be used to show that lambda is resolving. It was done by Lozevmor, Nekrasov-Shatashvili for the current group. I can show if you're interested. I have no time. And then I've done it for the Lichnerovich co-cycles, but again, the formulas are not nice. So here, lambda. But yes, we can integrate. Maybe I will say what is the Lichnerovich co-cycle. So we are the group is the group of volume-preserving diffeomorphisms, the Lie algebra of divergence Lie vector fields, and psi eta is the and every closed to form eta gives us a two co-cycle on the Lie algebra of divergence Lie vector fields. The period group is discrete, so we can apply the previous method with, and one can show that it integrates to a central extension of the universal cover of the group of volume-preserving diffeomorphisms. In my last, I started a bit later, because I still have this integration via prequantization. So the idea is to have a Hamiltonian action for an infinite dimensionally group on M, and then the pullback of this central extension would give central extensions of the group. Even so, here in this prequantization extension, so together with Karl Hermann, we showed that even if M is infinite dimensional, so this is just a group extension, but pulling back to a nice via nice Hamiltonian action, one gets smooth D group extension. So what is the prequantization extension? On the Lie algebra level is just taking functions, Hamiltonian functions to Hamiltonian vector fields. M is connected, so the kernel is R. And here we get the Hamiltonian group and the quantumorphism group has Lie algebra C infinity M. The quantumorphism group, or is identified with it, is given by those automorphism of the prequantum bundle that preserve the theta, that preserve the connection one. E is the prequantum bundle over M, connection preserving Newtonian. And we can apply it to cocycles on the, I know how to apply it to cocycles on the, for divergency vector fields and for exact divergency vector fields and for Hamiltonian vector fields. So what are the central extensions of the algebra of divergency vector fields? One can one knows what is the Lie algebra cocycle of this perfect Lie subalgebra of exact divergency vector fields. It's H2 theorem of M. So we showed with the Bas and with Leo that it is really a universal central extension. So the Lichnerovich cocycles I showed you before are the only relevant ones. So this was conjectured by Roger years ago. And we can integrate we can use the prequantization extension, a Hamiltonian action of our group on M. What is M here? A connected component of the codimension 2 Grassmannian. The idea came from Ismagilov, but with Stefan we proved that it indeed has we constructed the prequantum bundle so that we can apply the prequantization extension. That prequantum bundle can be obtained also with differential characters, with transgression of differential characters to the nonlinear Grassmannians. So there is another way to get the prequantum bundle, and again, so this was in a joint paper with. We still don't know if any two such prequantum bundles will differ by an element here in H1. We still don't know if this coincide or not, or how they are related, these two constructions. But there exists so that we get central extensions for the group of exact volume preserving diffeomorphisms. And now one can do similarly, but only partially, for the group of Hamiltonian diffeomorphisms. So now we are on the symplectic manifold. Again, we know the universal central extension for the Lie algebra. And that's hence every the relevant cocycles, as these Roger cocycles, constructed with closed one forms. H2 of the Chevalier-Eilenberg cohomology of X is first the RAM cohomology on M. So alpha here is a closed one form. And the difficulties here is that the cocycle is constructed not with the Hamiltonian vector fields, but with the Hamiltonian function. So actually, it's a cocycle nicely written on the Poisson Lie algebra. And we showed that the integrability, we know the integrability for certain Roger cocycles, namely those that come via a prequantum bundle. Here we had a prequantum bundle, theta is a contact form, the volume form, and so the idea there is that in this way we can view the Hamiltonian group, but actually the extension quantumorphism group as a subgroup of volume preserving diffeomorphism, but not on M, but of P. Here we know we have integrability criteria, so we get integrability criteria for here, and this is the result that in the we know which closed one forms give us integrable Roget cycles, namely those that come from two forms on P. So these two forms will give Lichner-Roche cycles. Pi, this is the fiber integration, and V is the volume of the total volume of the volume form. So we get only a partial lattice in H2 theorem. We don't know about the others. So this is the difference from the divergence from the volume case where we have a full lattice of integrable cocycles. And here with this method, we get only, sometimes we get nothing, sometimes we get everything, sometimes we get, just for instance, for the just a partial one. So this is an open. And,